respected faculty member. I am T. Rakesh from Tribal E Department, 3rd year, bearing roll number of 20955A0227. In power system analysis subject, my concept video topic is swing equation. First of all, the contents are introduction and what is the power system stability and the stability limit and why transient stability is limited. Why transient stability limit is lower than the steady state limit, and the rotor dynamic power system and the swing equation and the swing curve and the conclusion. Let's get into the introduction. In the power system analysis approach says the power system consists of lot of devices interconnected to each other. Although stability at every point must be common for all those devices, here each and every device have their own protection for transient. Stability of any system can easily be calculated from the generator or load side also. Power system stability. Power system is a very large complex network consists of synchronous generator, transformer and switch gears, etc. Basically, if the fault occurs in the system, the synchronous may break and will affect the whole line from generator to the load side. So the stability criteria is most important here for removing all the false condition and make the system stable and approach the operation for all the machines and whole power system. The power system stability is ability of the power system to retain the steady state without losing the synchronism. Usually, power system stability is categorized into two steady states. First one is transient and second one is dynamic stability. Stability limit. The stability limit is the maximum power that can be transferred in the network between sources and the load without losing synchronism. The stability state limit is maximum power that can be transferred without the system become unstable. The transient stability limit is the maximum power that can be transferred without the system being unstable when the sudden or large disturbance is occurred. If an increase in field current or adjust in the speed settings occurs in the simultaneously with an increasing the load, the use of automatic voltage regulation and the speed. A synchronous machine is a rotating body. The laws of machines of rotating bodies are called applicable to it. The kinetic energy of the rotor at synchronous machine is K is equals to half J omega S m square into 10 to the power of minus 6 mj. Here J is equals to rotor moment of inertia kg per meter square and WSM is equals to synchronous speed in radians. But Ws is equals to P by 2 into omega Sm. Here P by 2 omega Sm is equals to rotor speed in radians and P is the number of poles. And kinetic energy is equals to 1 by 2 J omega S into 2 by P square into 10 to the power of minus 6, where M is equals to J into 2 by P square into 10 to the power of minus 6. The moment of inertia Mj is sections by radians. We shall define the inertia constant h such that Gh is equals to Ke is equals to 1 by 2 m omega s to mj. M is equals to 2gh by omega s is equals to gh by pi f into mj, sections per radians. Swing equation. The figure shows the torque, speed at the floor of mechanical and electrical power synchronous machine. It is assumed that the voltage, friction and iron loss torque is negligible. The differential equation governing the rotor dynamics can be written as J d square theta m by dt square is equals to Tm minus Te Nm, where theta m is equals to angle in radians and Tm is equals to turbine torque and the Te is equals to electromagnetic torque, which is developed in Nm. While the rotor undergoes the dynamic as per the equation, the rotor speed changes by insignificant magnitude for the time period of interest. that is 1 second. This equation can be converted into more convenient power from by assuming the rotor speed to constant at synchronous speed. Multiplying both sides of equations, we get s j omega sm is j omega sm into d square theta by dt square into 10 to the power of minus 6 is equals to Pm minus Pe. Here the Pm is equals to mechanical power and Pe is equals to the electrical power. Rewrite the equation. J is equals to J into 2 by P whole square omega s into 10 to the power of minus 6 dt square d square theta by dt square is equals to Pm by Pe. It is more convenient to measure the angular position of the rotor with respect to the synchronous rotation frames of reference. This is the swing curve. As you observed here, in y-axis we can take the output, in x-axis half of the x-axis is having transient stability, transient wave, and the another half of this time stability and steady state stability, and x-axis we consider as time. And why the transient stability is lower than the steady state stability? If the system experiences a shock by sudden and large power changes and the violent function fluctuations of voltage occurs, consequently machines or group of machines may go out of step. The rapidity of the application of the large disturbance is responsible for the all loss of stability. Otherwise, it may possible to maintain the stability of the same large load is applied gradually. Thus, the transient stability limits the lower than the steady state limits. And the conclusion, hence, the equation is very helpful to determine the steady state stability conditions of the complex power system through calculate the angle and also having the equal area criteria. So any kind of transient can be eliminated from this. Thank you.